In this lecture, we are going to learn how to create a new project in Altium. So for that, go to the File menu and select New, and under that select a new project, and it will show you this dialog, that is a new project dialog. And here we have few options. We have option for PCB project, we have option for integrated library. So these are project type, what type of project we need. So in general case, when we are designing a PCB, we will use the first option, that is the PCB project. On the other hand, when we are creating the library of symbol or footprint, then we will use this option, that is the integrated library option, this one. So when we are creating a new footprint for a specific component, any electronic component like resistor, capacitor, diode, etc., then we have to choose this option, that is integrated library option. After we have created the footprint and symbol for those components, we can easily drag and drop them from the library to our sheet. So these are the two type of project that we can create in Altium. So let us begin with a PCB project, and here we have few templates for PCB. We won't be using these templates, ready-made templates, but we will be using a blank template. But you can create, use these or create your own templates also. So in most case, we will use this default option. We will not use any ready-made templates. And then we have to fill out this form. Here we have the option for name of our project. Please give a meaningful name here, and this one is the create project folder. So this is the option. If you want to create a new folder for your project to keep all the files of the project, then please enable this option. If you have already manually created a folder for your project, then you don't need this option, then you can uncheck this option simply. Then we have the location of our project, where we want to keep the project in our hard drive. And then we have the type of project. We have regular, VCS, and managed. Most of the time we will go with regular. So please give a descriptive name to our project so that you can later recognize the project. And let us have a look at the default naming of the project. So here they are not using space, so they are recommending underscore. So in our project name, we will use the same convention. We will not use any spaces. In place of space, we will use underscore symbol. So here I have filled out the form. I have chosen this name, that is relay board. So in this example, we will create a schematic for a relay board. We can just hit OK to create the project. It will take some time, and here it will, in the projects pane. So here in our project panel, this is a panel. We can move this panel also like this, but generally by default it is docked here like this. Dock it here, not in the top, but drag it like this. So this is the default layout, and we can see various projects here. And this one is our new project, that is relay board, and we can see that no documents added. So to create a schematic, first we need to add a schematic document to this new project. For that we can right click here like this and add new to project and select schematic. And we have various other options also. So what we have PCB. So when we will convert the schematic to PCB, we will choose this option. And we have other option like BOM, this one schematic library. So libraries will be added when we will create an integrated library. So this one will contain the schematic symbols, and this one will contain the PCB library or the PCB footprints of the actual components. We can also have via library, CAD CAM documents. So these are optional. The most important option here are schematic, PCB, and schematic library and PCB library. These four are most important, and we will be dealing with these four most of the time on most of the projects. So let us add our schematic. We have source documents and we have sheet 1. So we can see that the name is not so beautiful, or any, it is not descriptive. So let us save this, and It will go inside our project folder. Here we can give a meaningful name like relay board, like this. We have just remove the extension because this one is our project file, okay, and this will be, this relay board will be going to be our name of our this thing schematic file. Now we have a little asterisk over here. So this indicates that our project file is not saved. Our schematic is saved, but our project file is not saved. So this project file contains the information about how many files are inside it and which files are there. So for that you can go and save all option. It will save, and this red symbol is also gone. So now our project is fully saved to our hard drive, and we have a relay board schematic like this. And now here is our sheet, the schematic sheet, and this looks familiar. We have some grid like thing here, grid like patterns, and we can see grid over here. So these are 10 units wide square, so the length is also 10 and this is also 10. So in schematic it does not matter what is the unit of this grid, but it will matter when we will move to the PCB. So it is kind of a logical unit, 10 unit, okay. It is not something like a physical unit, but this is a A4 template. Here you can see this is a A4 template, so you can easily print it out on a A4 size paper. Generally we use this template for schematic. This is the default template. Now on the right hand side of this Altium window we have the library panel. So this is the libraries panel. So here in the library we have various components, various electronic components that we can drag and drop in our master sheet to design our schematic. It has basic components like resistor, capacitor, transistors, diodes, everything. It has integrated circuit, and we can also make our own libraries. So we are going to discuss that in a dedicated video. Right now we assume that we are already having those components that we wish to place in our schematic, okay. So as we are designing a relay board, so it will be something like this, like this. So it will be having some relays, like 8 relays like this, and these are simple sugar cube relays, small relays that we can directly solder on our PCB. And over here we can see the indicator LEDs. Some LEDs are there, so they will indicate when the relays are triggered. And we will be having a shift register to control this relay, so that we can serially control the shift register from a microcontroller and then command the relays to turn on and off. And we will be having a driver for the relay, because microcontroller or the shift register pin cannot directly drive those relay. So we will be using a driver chip like ULN 2003 or ULN 2008, which has 7 or 8 drivers, okay. And over here we will be having screw terminals, and this will be connected to each of the terminal pins of the relay. And as we all know that relay have 3 terminal pins, like common, NC and NO, that is normally open, normally close. So we will be needing a library for these terminals, screw terminals, the LEDs, the resistor, the these relays, the shift register and the ULN driver. And we will arrange those on our sheet and then logically connect them using wires. So let us first place the components that we need to build this circuit. So the very first thing is the relay, and we'll go to this library. I have kept my relay inside this library, that is miscellaneous, and the short form is MISK. So here I have my library, that is MISK or miscellaneous. So here we have miscellaneous stuff, and the extension is .intlib, which stands for integrated library. So integrated library means it integrates both the schematic symbol, this one is the schematic symbol, and the footprint along with the 3D information also. So here we can see the 3D model, and here we can see the actual PCB footprint, the pads and the silk screen marking. And here we have the logical symbol that we place in the schematic, which is a human readable document. And this one is the product, our actual product. The PCB is the product which is derived from the document, schematic document. So all the connections are according to the schematic. But the schematic is easier to read by a human compared to the PCB, because PCB is a final product and the aim is not to read the connection. To read the connection we refer to the schematic. So we have all the three things integrated. That means the schematic symbol that we place in our schematic sheet, and we have the model, the 3D model, the 2D footprint, everything integrated. That is why we call them integrated library under Altium. Great. So let us find the component. So we can find, we have various miscellaneous components here. Okay, and here we have our relay SPDT, which stands for single pole double throw. It is a type of relay. It is the most common type of relay that we will be using. And here we can see the schematic symbol of the relay. So this, whenever we see this symbol in a schematic sheet, it represents a relay. This is not the actual relay, but a human readable form of the relay. In the same way we have the alphabets, we have the symbols. So the, as in the same way a book is made up of alphabets, various alphabet of a given language like English or Roman, in the same way the schematics are built using symbols like this. These are electronic components. So how to place it in the sheet? So for that we can simply click here and then drag like this. So you can see the schematic symbol coming to the sheet and you can place it in a appropriate location. But just make sure that the grid is 10 here. Just make sure the grid is 10. You can see grid over here. You can toggle the grid using the G key on the keyboard. So whenever you press the G key on the keyboard, the grid will toggle. Now the grid is 5, now the grid is 10, like this. 1. So the 1 is the finest grid, then we have 5 and 10. So make sure it is 10 always, most of the time while drawing the schematic. So why it is? Because most of the pins like this. So these pins, now let me tell you first how I zoomed here. Okay, so for zooming into the schematic sheet, what we have to do, we have to place the control key on the keyboard and then use the mouse wheel, rotate the mouse wheel up and down. So moving it upward will zoom the document and moving it downwards will zoom out the document. So you will see that these pins, these are pins, these black things are pins which can be connected to wires. So these are also pins. So these are usually placed in this 10 grid, 10 unit grid. So this one is here, so this one is empty and we have here. So this is now a multiple of this 10 grid. So we have 0 here, 10, 20. That is why everything, this pin should always come in the grid. So here you can see light grid lines. So these are the grid lines. So pins should fall in the center of this grid lines like this. If it is off grid, you will having trouble connecting these pins. Okay, so make sure the grid is 10 and the pins are like this. So if the component is off grid, you can just right click here and align it to grid using the align command also. Okay, so for that just select the component like this. So you can see a green rectangle surrounding this component. That means this one is selected. Now we can right click and go to the align option, and from there we can align it to grid like this. So if some components become off grid due to this change in this grid, you can always make them align to the current grid using this option, align to grid, like this. Great, now we have our first component here. In the same way, we have to drag and drop all the components that we need to build the specific PCB or the circuit. Now let us see how to move and rotate components. So when you drag a component from library to your schematic sheet, it must not always be in a correct position or correct orientation. So what to do in that case? In that case, we can easily move and rotate the component to our desired orientation so that we can beautifully draw our schematic. So now let us see how to do all this thing. That means moving component and rotating component. So moving is very easy. Just select the component. This green rectangle will appear. And now using the mouse, you can simply drag the components to the desired location in the schematic sheet. Let us move it like this, And now how to rotate this component? Just select this component, this green rectangle, and go to the edit menu, and from there go to the move menu. And from this move menu we can do all this thing. That means we can rotate our component. So here we can see rotate selection clockwise. So this will rotate counterclockwise or anti-clockwise, and this will clockwise. And you can also notice the keyboard shortcut, and the shortcut is space or shift plus space for clockwise. So here it is, select the component, just keep on pressing space, and this component will rotate like this. Great. Now we know how to move and rotate the component. Now we need to place this component, that is the screw terminals. And for that I will go to the library, that is terminal. I have created this library myself. This is not a standard library, and this is an integrated library again. And inside this integrated library we will find many types of these connectors. So let us drag this three-way terminal, because we will be needing 3 pins. One for common, this one, the center one, and one for NC or normally closed, and another one for normally open, NO pins. Like this, drag it, rotate it like this, so that it is in this orientation. And this is the designator, and currently it is having a question mark here. That means it is an invalid designator. So in the annotation phase they will receive the actual designation, that means something like CON1 RL1. So in place of this question mark a numeric value will appear. For time being, just move this, that means this designator here, because here it will cause problem in the connection when we will place wire from this terminal pin to this relay pin. Great. Now we will move to wiring, how we will do the wiring. So the wiring, they represent the connection between two components like this, right here, between this connector and this relay. So we have to use, in Altium we have to use wire to connect these pins. How to do that? We have, this is the standard toolbar, and here we have an option, this one, for this wire, place wire. You can see the tooltip, place wire. Or we can also go into the place menu, and from there we can also put a wire by selecting this command under the menu, that is wire. And there is another keyboard shortcut, and it is P key. P stands for place. So just click anywhere on your schematic sheet and just hit P key on your keyboard like this. So it will open up this menu. This is the place menu, and it show what things you can place on your component. You can place a bus entry, part, manual junction, power port, wire, net level, port, and everything. And from here you can also select wire. And alternatively you can press this P, and instead of going to your mouse to select this wire, you can simply hit W on your keyboard. So this W stands for wire. So what you have to do, you have to quickly press P and then W. It will activate the wiring command, and as soon as the wiring command is activated, your mouse pointer will turn to a crosshair like this. And whenever you hover your crosshair over a connectable point like a pin of a component, it will turn red like this. You can see it has turned red. Now it is black, now it is red, because this is a connectable point. And on a connectable point you have to click your mouse button, left mouse button, and it will activate wiring. A wire will begin from there, and again go to the termination point. Here also you can see that your crosshair is turning red, and here you can again click once and it will complete the wire. See, wire connected from this connector to your relay. In the same way, connect it like this. Take a bend here so that your schematic look beautiful like this and like this. Great, you have connected your first components in Altium. You have connected this terminal to the relay pins. Great. Now first let us learn one more thing, that is panning. Panning means how to move left and right and top to bottom throughout a document. So for that you just need to right click anywhere in the schematic sheet like this, and your mouse pointer will turn to a hand like symbol. That means it is holding your sheet. Now you can easily move it up and down by dragging your mouse up and down, and in the same way you can move it left and right by simply dragging your mouse while you are keeping the right mouse button pressed. That means you have to press and then drag. So in this way you can easily navigate through a zoomed document. Great. Now what we will do, we will make 8 copies of this part, that means the relay and the terminal with all its connection, because we need 8 relay, and this is a 8 relay board. It has multiple relays. So let us first move it here like this. So how I have done this, first you have to select everything. And how to select thing, it is standard Windows procedure. Just click anywhere in the sheet and drag, and it will start creating a marquee, a rectangular marquee that will enclose everything like this. And when you release your mouse button, it will select everything inside the marquee like this. So it will select the connector, all the connection and the relays. And in this way now we can move it and just like this to a proper location. And you can also make copies of this by right clicking it and selecting copy. And again the keyboard shortcut is standard Windows, that is Control plus C, and paste is also very common, that is Control plus V. So first copy it and then paste it using keyboard shortcut like this. Make copies. Make sure you place it at regular intervals so that it looks beautiful like this. And after making 4 copies you can select all of them, and then it will select all the 4 parts. And again you can make a copy and then zoom out like this by pressing the control key on the keyboard and moving your mouse, clicking anywhere like this and moving your mouse. You can also do this using the scroll wheels, control plus scroll wheels. Copy, paste. Again put it at regular interval like this beautifully. 1 2 3 4 5 6 7 8. Great. Now we have 8 relay modules. Now we need to add a relay driver to this schematic, and we will use a Darlington array called ULN2803A, and it will drive all the 8 relay using Darlington transistor configuration. And I have that part in MISC IC or miscellaneous IC library. So where it is, this one, that is MISC or miscellaneous underscore ICs. And here I have lots of integrated circuits, common integrated circuits. And let us find ULN here. It is arranged in alphabetical order, so we'll find it here. So here we have ULN 2803A, and it has 8 inputs and 8 outputs. This is same as ULN 2003, but ULN 2003 has 7 output, while our this 2803 has 8 outputs. Now let us drag it from the library to our sheet like this. And here we have output and here we have input. So let us rotate this like rotate. Now it is rotated. What I have done, I have rotated this part in such a way that this out pin or output pins are close to these relays, because this will drive the relays. And this has inbuilt flyback diodes, so we don't need to attach diodes to each of these relay. It has inbuilt flyback protection diodes. So let us arrange this beautifully, something like this. And what we have to do, and these relays, so all these relays are 5-volt relays. In the actual production we will use 5-volt relays. It has 2 terminals for the coil, so we need to put 5 volt across this coil to activate this relay. So first what we will do, we have to connect each of the pin to the out pin. So again we will create wire using the wire command P plus W. It will start wire command. We'll click here, click here. So now we have connected our first relay. So this will, the output of this Darlington array is going to the relay like this, and second one will go like this. Like this. All of the pin we have to connect like this. I am clicking here on one of the pins of the output pins of the IC. Then I am creating a wire. Then I am taking a turn here by clicking here. So whenever you click here, it will put a edge there. It will put a bend there. So now you can bend it like this and go here. Great. So we have connected all 8 outputs of this integrated circuit to 8 of this relay. Now we have one pin of each relay left. So what we have to do, so this will provide a ground connection. So ground will flow from here through this IC to these relays. Now let us connect the common all like this. This is the common or ground, the return path for the current through the relays. Great. And now we'll learn one important concept about the power. So first let us end this wiring command. To end any current command, you have to press escape key on the keyboard and it will end the command. So let us learn about power supplies. So in the toolbar, this main toolbar, you can see these things. We have ground, we have VCC. So first let us get ground. Just click here and it will become attached to your mouse pointer. Just put it right below this ground pin so that we can directly connect it like this. Now press escape to end this command and then activate the wire command and connect it like this. So now we have connected this pin to ground, and ground is a type of power supply pin. In the same way, we have VCC or the positive supply here. Click it here and we need VCC here on these pins. So just put it like this. Okay, great. And now what we have to do, we have various VCCs in a single schematic. They all have different voltages. So this one will be 5 volts. So we will rename the net to 5V like this, 5 volts, so that it represents 5 volt here. Great. Now what we have to do, we have to again activate the wire command, place wire command, connect it here. So it is moving like this. Just click here once and here. So now all these pins, that is pin 2 of the relay, will be receiving 5 volt from here. Now if we open the data sheet of this integrated circuit, that is ULN2801A, actually it is ULN2803A. So we will see these are the flyback diode and it is connected here, common freewheeling diode. So this we need to connect to the positive of the relay. So here we are having the positive of the relay. So again the wire command, bring a wire from here to the common pin like this. Great. And now you have to understand one important concept here. So we have placed this thing here, a symbol for VCC and a symbol for ground. So these are not going to magically generate 5 volts somehow. So these are just plain names given to this net. So this nets means the connection. So somehow you have to create some means to generate this 5 volt. So this could be something like this. We can have a connector here. And this could be something like this DC jack where the user can plug a 5 volt supply, or a screw terminal like this where user can screw up the wire from the power supply. So we have to provide this. So again in the terminal section we have to do something like this. We have to use a two-way terminal like this, and we have to make one of the pins positive. So how we can do, we can just copy this thing here from here to here like this and then connect it using wire like this, and same we have to do for the ground connection like this. So we have a terminal where user can plug in power from a power supply and it will connect to this. And here one important concept comes. We don't have to directly connect using wire these two pins. we it can be done using net names the way I am doing here. So this is also this net, the name of this net is also 5v, the name of this net is also ground, so it will connect it to all the nets which we place like this, name like this, ground like this, and symbol like this. So we don't have to make a physical connection here, it will logically connect to these points. But while creating the PCB we have to create actual track from here to here. This is just for human understanding. Now let us get rid of this, and now we have to place a shift register here for controlling these ULN IC, and through this driver IC, this Darlington driver IC, finally we drive our relays. So let me tell you how to search for a specific components in your libraries. For that, use the search button here, and then we have these options. So we can search in name, note, orientation, everything. So most commonly we will search in name, and the name of our shift register IC is 74HC595. So I will search for this shorter term, that is 595, and I will change this thing, that is operator. I will by default it is equal, I will make it contains, so it does not fully search this thing. The name should contain this text. So this is a more generic, more general way to search. And now click search here, and you will see that the default library, it will become query result. So from query result you have got these components. We have 74HC595 that we were looking for, and we have two options for this. We have SOIC and DIP. So let me tell you one thing, that these are not present in the default library of Altium. These I have created myself, and I will distribute you this library which contains these items. So just drag this SMD1 from here to your schematic sheet like this. Now we have a driver IC, a relay driver IC, 8 channel relay driver IC, and a 8 channel or 8 bit shift register we have here. And you can see the inputs are here and the outputs of this 595 is here. So what we have to do, we have to flip this component in the X direction. So we cannot rotate it, because if I rotate it, then this let me try to do rotation first. So what will happen, this VCC will come to the bottom like this, after second. So after two rotation you will see that my ground is on top and my VCC on bottom. So this is not a good convention. The VCC should always be at the top and ground should be at bottom. And one more problem is there, that this Q8 now is in top and Q1 is in bottom. So let me undo it. So initially it was something like this, it was like this. So to solve this problem we can simply flip it. To how to flip a component, so just click and then drag. So it should be in dragging position, and while dragging, that means you don't have to release the left mouse button, just keep it pressed like this and drag, and at the same time press the X key on keyboard to flip it in the X direction. You can see the VCC is still on top, the ground is still at the bottom, just it has turned left to right. So now these output pins have came to left from the right position, see, like this. In the same way you can also flip it vertically using the Y key. Now let us see on which library this component was present. So double click it, and here it will show you the library name here. So it was found inside MISC IC or miscellaneous IC. Great. So you can also do this manual way, that if you know that this IC is present in miscellaneous IC, so all the miscellaneous or mixed type of ICs are present in miscellaneous ICs. So if you want some miscellaneous IC, you can directly go there. So this is miscellaneous, not this one. We have to find miscellaneous ICs, this one. So inside this library you will find all sorts of commonly used libraries, and this will also contain our ULN and our which one, this 595 IC. So here we have our 595 IC present inside. So from here you can also drag like this. If you know exactly where to find the components, on which library that component is present, so that is why I have hierarchically sorted out the components, all the different types of electronic components, and placed them into a library that you can easily identify. For example, all terminals are inside terminals, switches are inside switches, connectors are inside connectors, relays. We have SIMCOM, which contains all SIMCOM models like this. STM32, which contains all STM32 microcontrollers, common STM32 microcontrollers. Now we have to do the wiring, means the output from here to here. But before that, what we have to do, we have need to supply power to this circuit, this integrated circuit or IC. So just copy this from here and paste it near the VCC pin like this, but change it from 5 volt to 3.3 volt, because this is the voltage range in which our microcontroller is operating. That means our STM32 is operating. This is the common voltage for our microcontrollers. So now the name of this net has been changed to 3.3 volt. Ground is same, common ground, like this. Now time for connection. Use wiring methods to connect all these like this. And all digital ICs like this also need a decoupling capacitor placed near its power supply pin. So we'll find that decoupling capacitor in our X basic library. We will use SM. This SM stands for surface mount. So SM capacitor is a surface mount capacitor, and this TH capacitor is a through hole capacitor. So we'll be making using a 0603 size capacitor. We also have bigger 0805 and 1206, but for this design we will only use 0603 components. So we can just drag a ceramic capacitor from here, and the values, the default value is also okay, 100 nanofarad. This is the most common value that is used for digital IC decoupling. Rotate it like this and connect it to the VCC pin of the microcontroller like this, and the other end will be connected to ground like this. Great. Now our aim is to make our relay board compatible with this STM32 Ethernet development board. So over here on the top left hand side we have the outputs for the shift register. So inside this PCB we are also having a shift register. This is SOP16 here. I think this one U5 or IC5. So this register is used to control all these bicolor, that means red and green dual color LEDs. These are diagnostic LED, and the same the output from this LED, that means the shift register. So this shift register is controlled by these signals, that is we have data, we have clock, we have latch, and we have a OE or output enable. So all this line control this shift register. So same parallel connection and the cascaded data out connection. So all the connection, the clock, the latch, the OE, these are parallel with this shift register, but this data out is in a cascaded form. So we can easily cascade more shift registers to the same signal without wasting the GPIO pins of the microcontroller. So only 1, 2, 3, 4 GPIOs are required to control this shift register, and it will control these 3 or 4 bicolor LEDs. Actually this one is not controlled by this LED, is not controlled by the shift register. These 4 LEDs are controlled by this shift register, because the shift register is having 8-bit output and one LED required 2-bit to drive, one for the green channel, one for the red channel. So in total we need 8 channels, and then the cascaded output from this shift register is available here on this header, that is con3. So our aim is to make our relay board compatible with this connector, so that we can plug a header or wire here, and from there we can connect our relay board and place it next to this PCB and control our input output relay board through this shift register without wasting the precious GPIO pins of the microcontroller. So for that we need to place a connector here in our new PCB, new relay board PCB, and it is available under JST or Japan solderless terminals. So we need a 6-pin JST header. So just drag it from the library to your schematic sheet somewhere close to this integrated circuit, this IC. And now we have to make connections, but the connections should follow this exact same order like this. So the first one is 3.3 volt, then we have output enable, latch, clock, data, and finally ground. So the top one is 3.3 volt and the last one is this ground. So I have done the connection for 3.3 volt and ground. Then we have OE after 3.3 volt. So this pin 2 must go to output enable. Then latch, and I think we have latch, then clock. So it is going in reverse order. So I think it is better to flip this terminal so that we have an orderly connection from here to there. So let us disconnect. To disconnect we have to select the wire like this and select the delete button on keyboard. Simply delete both of this connection. So this ground should go to the top. Ground should not go to the top. We will do connection. The pin 6 should go to this one and this should go down, or better let us drag it somewhere here. Let us hide this mail header. We have comment mail header uncheck visible like this. Put it here so that it doesn't come in the way. So this first pin is actually ground and the sixth pin is actually 3 point. This is looking much more cleaner and this should go to output enable. After this pin 5 should go to output enable like this, output enable. Then this is going to latch, but let us cross check that. First we have 3.3, then output enable, then latch. 3.3 volt output enable and latch. After that we are having clock. This is a straightforward connection. Then we have clock, then finally we have data, and after that we have ground. So we have verified these three pins, that is 3.3, output enable, latch, and after latch clock, DIN and ground. Then clock, DIN and ground. So actually this is D out from this board, so it should go to the DIN of that board. Great. Now let us connect this reset signal. So as we can see, it is an inverted signal. That means it is having a bar over its name. That means reset is asserted when this line is pulled low. Low because due to this inversion of signal. This is inverted signal. That is why it is activated by ground level or zero level. So to reset the chip, we need to ground it. So to keep it in normal operation, that is without reset, we need it to connect it to VCC or 1, logical 1. So let us place a wire over here like this so that our chip is not in a reset condition but in a normal working condition. Then we need few resistors here. So let us open our XBasic library and get some SMD resistors. SM res 06. Again the resistors will also be 0603 size. Sorry, not the LED but the resistor. So this SM stands for surface mount resistor 0603 size. Let us get rid of this LED and let us change the value to about 4.7 kilo ohms. Oh, like this, and we will use these resistor to apply proper logic levels on this pin when the MCU is disconnected or MCU is just starting up. That means all these pins of the microcontroller are in high impedance state. They are not still converted to output state. So in that case these pins will be floating, and floating levels are not good. So we will keep important levels to some definite values. Like the very first thing is that this output enable. So we will make it again, you can see that it is a inverted signal, that this OE is inverted. That means output is enabled when this pin is pulled to ground. So we in that case this outputs will be enabled and either low or high values will be present here. So when the micro and but when the microcontroller has not started, it will contain garbage value and it will trigger the relays randomly. So to avoid this situation, we will make the outputs disable initially when microcontroller is not connected or it is just starting up. So when these are invalid values, these lines will be having invalid levels or they will be high impedance. So in that case we will keep this OE to a definite level. So just connect from here to, so we'll keep it logic high by using a resistor connected to OE. So here just notice these dots. So these dots signifies connection. So the wire coming from here is not connected here, not connected here, also not connected here, just connected here. You have to pay attention to these junction dots. We need one more resistor, and what we will do this time, we will place it near ground and we will connect it to the clock line, something like this, so that my clock line is sitting and does not fluctuate. It should not fluctuate, it should be cleanly connected to ground or zero level like this. And for beauty we will keep both this ground at the same level like this so that it looks nice. Great. Now we'll also connect these output pins one by one. So in one, the input 1 of this Darlington array will connect to Q1 or the output 1 like this, Q2 like this. So we have all the 8 outputs from this shift register connected to the respective input pins of this Darlington array ULN 2803. Q1, Q2, Q3, Q4, Q5, Q6, Q7, Q8. In the same way, in 1, in 2, in 3, in 4, in 5, in 6, in 7, in 8. Great. Now we need to replicate this connector. We will be needing two such connector in this PCB. Why? Because one will be for the input. So from the microcontroller we will be receiving these signals and it will be operating this shift register, and this shift register will be operating this relay through this Darlington driver. So but in this design, this entire design should be cascadable. That means multiple number of these PCBs should be can be connected to each other to increase the number of outputs. For example, if you need 8 outputs, then you can use one PCB or one card. On the other hand, if you need more than 8 outputs, then you can cascade another PCB, a similar PCB, in a cascaded manner so that the output from first PCB enters the input of second PCB. So we will be needing two such connectors, one for input and another for output for cascading. So just copy this connector and place it somewhere, I think like this. So one is the input and one is the output. So we should also label this. So for labeling we will place a text. For that we will go to the place menu and select text option, text string like this, and name this one input. Okay, this one will be, this connector is input, and name this output like this. So we are having two ports for cascading. So when we connect a next PCB, then output from here will be connected to the input pin of the next PCB. So it will be having parallel signals like this. We can have, everything will be identical. Now we need to connect these signals, that means clock, latch and output enable, to this connector also. And for that we have two options. We can simply connect wires to these pins like this and use net labels, or we can directly connect it over here. So I think this will look much cleaner, so we'll use net labels. So here is the icon for place net label. It is also available under the place menu, net label, or you can place it using the P key on your keyboard and then selecting N for net label like this, and we will label it like this. We will leave the D in pin, we will have the clock pin, so we'll name it CLK for short, and we'll put it on this line. So you have to put it like this when the crosshair turns red like this. So now the crosshair, you can see it is black or gray, but when you hover over a wire it will turn red. So just make sure you are connecting it to the clock line like this. Put it here, clock, and same clock put it in the third pin here also, so it will make a connection between these two. Then hit the tab key to change the net label, and this time we will make it latch. The short form of latch is lat, like this one is latch, this one is latch. Then what we have, OE, we have OE, we have OE, we have OE, like this. Now only one pin is left, that is the data pin, but the data pin is not connected in parallel like the clock, latch and output enable pin, but it is the cascadable output. So the data that is coming out from the shift register, that is S out or pin 9 of this IC, must go here. Let me make some room for the wire. Now we can easily take the wire from here. So if you make a wrong turn, then simply press backspace on your keyboard and it will delete the last point like this. Great. So we have S out coming, so data is coming from this pin, that is pin 2, it is entering here, and when it is shifted to all these 8 bits, then the extra bit is coming out from here. So this allows cascading. So to know more about this cascading, please refer to the data sheet of this, that is 74HC595, or consult some tutorial on this shift register so that you can understand this. Now we need to put some indicator LEDs so that we can know that when and which of the relay is turning on or off. So from the X basic library I will use a through hole LED, because this through hole LED, they are bigger, and when you make it, the put your PCB inside an enclosure, this LEDs look good. So I will choose a through hole 5mm radius LED. So here we have TH for through hole LED 5R, that means 5mm radius, because we also have 3mm LEDs. That is why I have put this term, that is 5R, so that we can know that 5mm radius LED is this and 3mm is other. Now we have the LED, we don't need this value, so hide this. So in the comment field you can also put that color of this LED, green or red, whatever you need, so that when we generate BOM or bill of material, we know what color LED to put here. We have the LED, and we will connect the LED over here to the output of shift register, not to the this output. This is 5, so this is, but this time we will also use net labels to connect the LED to these pins. So we will put net label over all of these pins. So just go to net label and we will name it something like this, SR for shift register, SR underscore Q1. So this Q1 signifies output 1, and let us also copy this thing so that we can easily replicate, put it here. So you here you will notice excellent feature of Altium, that is it is automatically increasing the net label name for example, the first one is Q1, it is automatically making the second one Q2, Q3, Q4, Q5, Q6, Q7, Q8. So this make our task very easy and also very fast. Now click escape or hit escape key on your keyboard to get rid of this placement mode and go to normal mode. Now we need 8 such LEDs, so we will copy and paste the first one. Just select the LED and copy it, paste it like this. And once we have 4 LEDs, we will again copy all 4 of them and paste it once again like this. Now move it to a suitable place on the sheet so that you have enough space for wiring and resistors. And now we will place the series current limiting resistor for these LEDs. For that we will copy this resistor and paste it here. We will change the value from 4.7k to 330 ohms or 330 R, because we don't generally have the ohm symbol on keyboard, that is why we use R here. Now let us connect this like this and copy this thing resistor also 8 times. So what I am doing, I am pressing Ctrl plus C to copy this resistor and then Ctrl plus V, which is the standard copy and paste commands on Windows like this. And connect the cathode of all the LEDs together like this. So I am connecting the cathode or negative of all the LEDs together like this. And finally I will connect them to the ground. Place wire to the ground. Now we have our 8 indicator LEDs. Then we will create wires here for net. Click here, double click here and right click to terminate. Click here to start wiring, go up to here, then double click here to put a point and then right click to terminate the command. You can also change the size, so this one is shorter, so you can just drag this thing here, this handle. Great. Now we'll copy net labels from, let us move it like this. Now copy net level from here, Q1, or simply place net label. Now it is 9, change it to 2, again 2, 3, 4, 5, 6, 7 and 8. You can also move this net level like this. Great, so now we also have the indicator LEDs. Now we almost have everything that we need in this circuit design. To finalize this design, we will put the mount holes and the fiducials. So the mount hole in the PCB help mount the PCB to external cabinet or enclosures, and we have that inside our XBasic library again. So go to XBasic and find mount hole. It is somewhere near the end. We have mount hole 3 millimeters. So the diameter of this hole, this diameter of this hole in the PCB will be 3 millimeters. So this is kind of standard screw size for small PCBs. We'll drag one of it from the library, and then what we will do, we will make 3 more copies like this, because generally in our PCB we have 4 mount holes in the 4 corners of the PCB. If you need more or less, you can do so. And after the mount holes, we will require fiducials. So where is my fiducials 40 mils. So hope you know what is a fiducial. So they are marking on PCBs that help automated pick and place machines for assembly and for alignment. If you don't know about these, please Google it. So these are called fiducial marks. So generally we have 3 or more fiducial mark in our PCBs. Generally in SMD PCBs, surface mount PCBs, that are assembled using automated process, automated pick and place machines. Great. And after this we need to do a annotation of this PCB. So what do I mean by annotation? So these designator, they are right now holding dummy values RL question mark question mark. So this question mark is just a placeholder. Now we need a process to convert this to RL1 RL2 automatically, not by manually changing the name. We can also manually change the name like RL1, but this is a very time consuming process. So better use a placeholder here question mark and do a automated annotation. For that, go to the tools menu and go to annotation, and from there select annotate schematic, and it will open up a dialog like this. So here we are having all our designators which are currently having placeholders, not having proper values. See all the question marks here. And now what we need to do, we need to click update changes list, so it will convert this to proper designator. Just see how it works. Update changes list, it will ask you that changes made, 47 changes are made. So this indicates how many components we have in our schematic. So it is telling 47 components or 47 new components are there. Because this is our first annotation, all the components are new only. That means all the components will get this designation or annotation. So later on when you do a second or third annotation, then this might contain smaller number. Only the new components that you add after the first annotation will be totaled here, counted here. Just click OK and keep your eye here. These question marks will be filled up with proper values. C. So previously it was C question mark, con question mark, question mark. Now it is converted to C1 and con 1, con 2, con 3, FD1, FD2, FD3. So all the components are now getting proper designators. But still now these changes have not been applied to your schematic sheet. It is just a proposal here. It is proposed changes list, so that you can inspect and verify if any mistake is there, or if you don't want to annotate any schematic this component, then you can simply remove this check mark, so it will not annotate it. But if by default all the components are selected here, and you can create accept changes. So these changes are okay, accept the changes. And now this is the engineering change order, or this is called ECO in the Altium. This is called ECO in short. Here they have written create ECO or engineering changes order. So remember all these terms, note it down somewhere. And finally we can execute the change, and when you execute the change you will see a tick mark appearing here. That is very important. So here it is also changing that how the changes will be made, and you can simply click execute and the schematic will be updated. Click execute change. See, so just scroll through the list after you click this execute change to see if any errors are there. So we cannot see any errors because the errors will be shown in a red cross mark, so it is very easy to distinguish here. We don't have any errors. We can simply click close, close, and see We have RL1, RL2, RL3, RL4, RL5. Everything has been properly annotated. U1, U2, R9, R6, everything is there. R1, R2, R3, LED1, LED, fiducials, everything is great. Now the schematic is fully ready to be exported into a PCB design. And now we will add one more document to our project, and this time it will be a PCB project. So right click here, add new to project and select PCB. So it will open up a black thing like this. So this is a blank PCB right now. So go to your schematic. So it will open as a tab here on the top. So you can, this will switch to PCB view and this will switch to schematic view like this. Now save this document using save all command and give it a proper name. Initially it will have something like this, PCB1, but this is not descriptive. So just get rid of this and enter relay board. Remove the extension, just relay board like this and click save. Now it is updated. Now we are all ready to export our schematic to PCB. So for that, just go to design menu and select update PCB document. And again it will open up a ECU or engineering change order. So it is asking you what components to add. So add, the first stage is add component. After that it will add nets. So net is the connections, and then some component class. So what are component classes, that we will look in later lectures. And we also have rooms. So right now we don't need rooms, so we can just remove. So we will have dedicated lesson on room in the later videos like this. So we initially we don't need room, so we will uncheck this. Component class is okay, don't remove the check. And finally just click execute changes. So this time also pay attention to success and failure here. So if any of the PCB, this schematic symbols, they are not having footprint, then it will throw an error here. So just click execute changes and see the check marks, and again move from top to bottom and to see any cross marks are here, red crosses are here. So if that is the case, but we are not having any errors in our export, so everything is exported properly, we can just get rid of this dialog by clicking close. And when we move to this PCB view, we will see something like this, all of the components exported here. See, now all of the, to pan left and right, click the right mouse button and move your mouse, it will change to a hand like thing. And now you can both horizontally and vertically you can move like this. Here you can see all the relays, the LEDs, the terminals, screw terminals. Some LEDs are here, some are here. LED 1 2 3 4 5 6. We have our ULN driver, everything we are having here. So that's it for this lecture. In the next video we will start creating the actual PCB design from the schematic that we have created in this lecture. So please stay tuned, see you there, and thanks for watching.